Nuclear proliferation. Why America has already lost this nuclear war. In 1945, America had the first fission bomb. In 1952, America developed the first thermonuclear bomb. The Manhattan Project was completely compromised by Soviet spying. In 1949, fission, Russia. 1955, thermonuclear in Russia. 1952, fission bomb in UK. The Manhattan Project was an international project. Several British scientists worked there. 1957, thermonuclear bomb, UK. 1960, fission bomb, France. 1968, thermonuclear bomb, France. 1963, fission in Israel. France and Israel worked hand in hand. This helped Israel keep their program hidden from the world view. China, 1964, fission bomb. China, 1967, thermonuclear bomb. China moved from fission to thermonuclear warheads faster than any other nation in history. Years later, China's intense espionage on America's nuclear program gave them the design for our most advanced warhead. India, 1974, fission bomb. Since the end of the Cold War, India, in 1998, did a thermonuclear bomb. Pakistan, in 1998, did 6 fission tests in 2 days. With nearly simultaneous tests, Pakistan proved to the world how far nuclear weapons technology had come since America tested the first fission weapon. Using subcritical testing along with the world's increasing knowledge of nuclear physics, many nations can develop capable weapons in secrecy. For instance, plutonium is one of the most bizarre chemical elements known. The Manhattan Project had to put enormous resources into learning how to shape and machine plutonium. Information such as that is now freely available on the internet. Why is so much information available? Because the chief scientist in Pakistan sold nuclear technology to Iran, Libya, and North Korea. North Korea, DPRK, exploded a fission bomb in 2006. They have used subcritical testing to accelerate their nuclear program. DPRK went thermonuclear in 2017. Once again, a country had success on their very first thermonuclear design. The world looks very dangerous when all nuclear powers are shown together. In fact, there are so many nuclear powers in the world that we are getting in each other's way. In a few minutes, we'll see how this has limited America's military options. Subcritical testing is complicated. A video from Sandia Laboratories about the National Ignition Facility's enormous laser array will help.
All 192 laser beams enter the whole ROM through 2 holes at the top and bottom and are precisely aligned to hit a particular spot on the inside wall of this little cavity. The laser beams then rapidly heat the inside surface of the whole ROM, generating an oven of energetic X-rays that is 6 million degrees Fahrenheit in temperature. Those energetic X-rays then start ablating the fuel capsule surface, compressing it at velocities of over 300 kilometers per second. During the final stage of the implosion, the fuel core reaches pressures of over 300 billion atmospheres and temperatures of 200 million degrees Fahrenheit. Under these conditions, nuclei of hydrogen atoms fuse together and create a microscopic star lasting 100 trillionths of a second.
When explosives are detonated around a pit, it's nearly impossible to see what actually happens to the plutonium before it goes critical and explodes. A piece of plutonium the size of a poppy seed in place of the fusion fuel allows scientists to see how the metal reacts to pressure and heat. This is subcritical because even the smallest nuclear explosion cannot occur with such tiny pieces of plutonium. Returning to the subject of how nuclear powers are getting in each other's way. There are 50 or so North Korean military sites that are known and publicized by America's military. These bases would be just the starting point of a nuclear strike intended to take out North Korea's nuclear capabilities. Using NukeMap will simulate a single Trident nuclear submarine warhead detonation. Without getting lost in the details, the deep red is going to be fatal to almost anyone who isn't in a fallout shelter. The orange and yellow areas can still kill people depending on how long the radiation lasts and how quickly the people can get into shelter and or get medical care. Each Trident sub can carry hundreds of warheads, so this would be salvo number 1. This would produce so much fallout practically every person in the country would die from radiation poisoning. Even one salvo is unlikely because no one knows how the wind will blow. It's clear from this simple example that America would be killing thousands or maybe hundreds of thousands of Chinese, Russians, South Koreans, and Vietnamese. China has been building a massive nuclear arsenal without interference for decades. Russia has a nuclear capability that is roughly equal to America's. America could possibly take out North Korea with a massive first strike, but we don't dare start a nuclear war with China and Russia. Every time another country becomes a nuclear power, America's ability to respond with a nuclear barrage becomes more limited. The chance of nuclear war goes up with every new nuclear power. The chances of America suffering a nuclear attack also increase. An even more direct threat is the ballistic missile arsenal North Korea has built, along with plenty of nuclear warheads. It's only 1,200 miles from a launch point in North Korea to Taipei, Taiwan. Only 420 miles to Hiroshima, Japan. Worse yet, only 80 or less miles to Seoul, South Korea. A salvo of a dozen short-range nuclear missiles would most likely overwhelm any anti-missile system, destroying a city of nearly 10 million in minutes. This is a war of high-altitude bursts. The hemp footprint over North America may be worse than what was described before. The hemp is likely to be many times more powerful, a super EMP. One of America's best bomb designers published information about creating a super EMP bomb as well as making the initial nuclear light flash brighter. Weather balloons. Weather balloons were used in dozens of atmospheric tests. Using NASA's modern balloon deployment as a background, we can see deployment of balloons and cargo is now much simpler, faster, and portable. They can be deployed in remote locations and can easily cross international boundaries. They are mentioned in many reference documents as a method of weapon delivery. Japan had so much success with them in World War II. The Sky Slice model shows weather balloons going all the way to the top of the source layer. Our most modern attack jets can't fly as high as weather balloons, requiring a high-altitude air-to-air missile to destroy. This declassified film is from Operation Plum Bob, and the test shot was codenamed Hood. Hood was a thermonuclear device tethered to a weather balloon detonated at 1,500 feet with a yield of 74 kilotons. The device was small and sized for this picture as a pink canister. America's nuclear stockpile has an updated, smaller warhead with a variable yield of 5 kt to 150 kilotons. The warhead weighs only 290 pounds, deployable from weather balloons. Hood was the largest yield atmospheric test in the continental USA. The nuclear flash was seen in San Francisco, 353 miles away, and over the Sierra Nevada mountain range. The blast wave was felt in Los Angeles, 241 miles away. Weather balloons are steerable by going up and down in altitude. Winds blow at different speeds and directions depending on the altitude. Hemp delivery method number 1 is weather balloons. Delivery method number 2 is short-range tactical missiles. There are so many countries with missiles that can carry a small nuclear warhead that it's hard to keep count. They are portable, can be hidden in shipping containers, and are solid-fueled so they can be fired on short notice. Delivery method number 3 is, of course, by satellite.
Fuse is a warfighter word indicating a weapon's detonation point on its ballistic trajectory.
We can watch as they pound and burn these warheads. Warheads must survive in a nuclear environment. These tests also prove warheads will not detonate accidentally. Sensors keep the fuse system aware of what's happening and what's allowed to happen at any point in time. Since the plutonium pit is wrapped in high explosive, it must not be triggered by fires from rocket fuel, jet fuel, or anything but the detonation signal from the fuse. Coming from a computer science background, this type of stimulus complexity is common in real-time applications. With nukes, there can be no errors, hence the billions of dollars of testing. Adding to the complexity, some nukes are ground-penetrating weapons. They must penetrate several feet of solid rock before detonation. This rocket sled is going to demolish a missile similar to how an interceptor missile would take down a short-range ballistic missile. The fuse knows it's not supposed to hit the ground at this point. An impact now will cause the fuse to activate its salvage circuit and detonate the nuclear warhead. Our sub-launched missiles hit at Mach 24, 4 times faster than a railgun projectile travels. Full detonation of a 2-stage thermonuclear device takes 17 microseconds. Even at Mach 24, the warhead only travels 5 inches in 17 microseconds. A laser beam can't take down a warhead at only 17 millionths of a second. In other words, a missile defense will cause a detonation and a HIMP at the point of contact. Once a balloon or a short-range missile crosses our borders, a HIMP is going to happen. 5 inches of damage on this missile barely crumples the tip of the nose cone. The warheads are hardened against radiation. The warhead can also detect radiation from another exploding nuke in ample time to detonate itself. Now you have 2 nukes going off at the same time. Now that we know the nature of the threat, it's easy to see that our border security is far more complicated. How does America patrol areas hundreds of miles from our physical borders? These are the 10 chapters in this video series. I will continue to release more videos and video series on this complex subject.